Here are some more examples using Stokes theorem. In this question, we're asked to use Stokes theorem to compute this line integral. And what it means to use Stokes theorem is to compute the surface integral in place of the line integral. So let me get a sense of what is going on here. I've got some vector field, and I'm looking at the curve of intersection of these two surfaces. That's what the line integral is being taken over. And I just need to come up with an appropriate surface that has that C as its boundary, oriented in the appropriate way, to compute a surface integral over. So I've got this, I guess, is a hyperbolic paraboloid. This is a cylinder. I went ahead and graphed these things so that I could get a sense for what the curve looks like. So the cylinder is the gray bit, and then the purple is the hyperbolic paraboloid. And you can see the curve here is this sort of it's going up and down around the cylinder like that. Okay, so I'm gonna maybe copy that image as best as I can over here. Okay, so the curve C looks something like this. And I would like to, let's see here, replace this line integral with a surface integral over a surface that has this at its boundary. And this is supposed to be oriented in a counterclockwise direction when viewed from above. So again, back to this graph, if I'm looking this way, right, at that yellow curve of intersection, it should be going counterclockwise like this. So when I replace this line integral with a surface integral over some surface, I'd like the surface to have its orientation upwards, its normal going up, because that will be consistent with this counterclockwise rotation on the curve. Okay, so again, back to the picture. I think what I'll do is take the purple surface, right? Just a piece of the purple surface. It's like this Pringle-shaped surface that has the yellow boundary. That's what I'm going to use as my surface. So that is the hyperbolic paraboloid. I have a Cartesian equation for it, and I can see if I can just cut off that surface according to the cylinder, which describes in the region in the xy plane, I'll have the surface that I want. So S is going to be this hyperbolic paraboloid restricted to basically this restriction right here, that x and y are within the unit circle. Okay, I'm probably not going to do a great job of drawing that, but you know, it's this kind of surface that is from the hyperbolic paraboloid making C as the boundary. That's what S looks like. Okay, and then I want to set up this surface integral over S of the curl of the vector field F dot ds. So this surface integral of the curl of the vector field. All right, well, some of these parts are easier than others, so let me actually move over here and compute the curl of F. You just take del cross F So I'm taking partial derivatives here. Just remember how that goes. For example, the first partial derivative I'm going to take is the partial derivative of xy with respect to y. X is held constant, so the derivative is x. Okay, so this vector field represents the curl of the vector field F. All right, I think I'm ready to set up my surface integral now. I think what I'm going to do to start is, since the surface is described as a function, so z is a function of y and x, I'm going to use the easiest parameterization I can think of, which is just letting x and y be the parameters themselves. And I'll tell you, when you do that, take a look at the surface. If you let x be the u parameter, for example, and y be the v parameter, then if you look at the RU vectors and the RU and RV vectors are pointing in direction of the x axis and y-axis, and when you take the cross product RU cross RV, it's going to be pointed upward. So that's exactly what I wanted to be consistent with the orientation of the curve along the boundary. So letting x be the u and y be the v is a good choice. And I'm just going to not switch variables and keep it as x and y instead of switching over to u and v. Okay, so like the curl of f, like I said, I'm keeping that in terms of the variables x and y. There's not much difference writing down u and negative v 0, right? And then what I want to do now is dot with usually ru cross rv, but I'm going to think of it as rx cross ry. Okay, so I've chosen to make x and y the parameters. Here is my curl vector field, evaluated those parameters, so kept in x and y. Here is rx cross ry, and I'm going to now set up the domain over which I'm integrating. So the x and y variables, as mentioned before, are restricted to the unit circle in the xy plane. So I'm looking at this double integral at the moment. I'm trying to integrate x and y over a circle. So it makes more sense to express the region D in terms of polar coordinates instead of representing it as like a type 1 or type 2 in x and y. So I'm going to do that. Okay, and here's my double integral to solve. All right, in this next example, we're going to verify that Stokes' theorem is true. What that means is to verify that a certain surface integral is equal to a certain line integral. So if I'm verifying Stokes' theorem, I'm actually computing both sides and demonstrating that they're the same value. So I'll go ahead and do the line integral first. So I'll compute the line integral and see that it coincides with the surface integral. Well, what line integral are we talking about here? We're looking at the unit hemisphere, like the right-hand side of it. Okay, like this. And the line integral, of course, would be the boundary region, which is this curve right here, just a circle in the xz plane. And let me get the orientation set. So they're talking about the surface being oriented in the direction of the positive y-axis. So the normals are all sticking out to the right. And so in order to make the orientation of the curve consistent with that orientation, I need it to go in this direction. And if you think of looking at the xz plane with the x-axis sticking out to your right, then this is clockwise rotation for the curve of the boundary. Okay, so that's C, and that's the orientation of C. Let's go ahead and try and set that up. Well, in order to parameterize C in the correct orientation, I need it to be going clockwise in the xz plane. So to do that, I'm just going to let x be sine and z be cosine. And of course, y is 0 because this is occurring in the xz plane. And I'll have t go from 0 to 2 pi. So there's the parameterization of the curve C. And to compute the line integral, I'm going to need the derivative. Okay, I think I'm ready to compute. I take the vector field and I evaluate it at the parameterization. And dot with r prime. I got a little bit more room, so let me go ahead and evaluate this out. I'll use a double angle formula here. Okay, and plugging in, I'm going to get negative pi. Okay, so apparently the circulation of this vector field in the direction of clockwise around the unit circle in the xz plane ends up being negative pi. So that's 1/2 of Stokes' theorem. in order to verify Stokes' theorem, I want to now compute a surface integral over the hemisphere surface of the curl of the vector field and see if I get the same answer. Okay, so let's compute the curl. So the curl of this vector field is -1, -1, -1. And I need to come up with a parameterization of the surface, and then I'm ready to compute the surface integral. Well, sort of the usual way to parameterize a sphere is to borrow spherical coordinates, right? So I think I'll do that. And I do need to pay attention to the orientation. I want the normals to be sticking to the right. So if I let phi be the u variable and theta be the v variable, that should work out, and here's why. If you increase the phi variable, it goes sort of down, tangent to the surface like this, because you're moving away from the positive z axis. And then if you increase the theta, then you're going counterclockwise from the positive x-axis, which will be going in this direction. And so if you make this u and this v, then the cross will stick out perpendicular to the right. So I think that's what I'll do. I'm going to let u play the role of phi and v play the role of theta. And this is a unit sphere, so I have the following. So there's my parameterization, and this is a parameterization that we've seen before in previous examples. So I'm just going to go ahead and jump right to the cross product, which like I said, we've seen before. Okay, and I also want to put the appropriate range on the parameters. I forgot to do that. So u is the phi variable. So if you look at this surface, we've got like North Pole all the way down to South Pole. So u is going to range from 0 to pi. And then since I'm only getting the right half of the sphere, then I only let the theta range from 0 to pi as well. And then I'm ready to set up the integral, the surface integral. Okay, and I'm getting negative pi for this surface integral as well. So that's a verification that Stokes' theorem holds in this case.